Let's do another absorption and stripping problem. So in this problem, we're trying to strip CO2 from a liquid solvent using air as the carrier gas. So immediately a few things stand out in this problem. The first is that we're using a cross-flow system. So the normal operating line equation with countercurrent systems is not going to apply. And the second is that the inlet liquid is 20.4% weight percent CO2, which means that we cannot assume that it is a dilute solution. So we're going to have to use mole ratios instead of, weight ratios instead of weight fractions. So if you recall, a weight ratio is equal to capital X is equal to X over 1 minus X. And instead of using the total flow rate, we're going to be using the inert flow rate to calculate our operating line. Let's draw out a cross-flow system just to show what it looks like. So in the cross-flow system, we have liquid flowing through as usual. And we have a series of stages, but the gas is actually split from the same stream and sent to each stage separately. So all of these stages have the same gas concentration, but they might not have the same flow rate. So in a sense, this is like several single stage operations, several flashing operations, for example, in series instead of a countercurrent system. All right, let's try to do a mass balance around one stage in order to see if we can derive an operating line equation. So around a single stage, you're going to have the entering liquid, which L, and as well as the weight ratio, Xn, and you're also going to have the entering gas at a flow rate G with a concentration Y naught. Now exiting, you're also going to have the liquid flow rate as well as a new ratio. Same thing for the gas here. So Yn plus 1. Now, because we're using weight ratios, we don't have to worry about the flow rates because the flow rates will always stay the same. So we can just completely disregard that. Now, let's try to do a component balance here. So the inlet streams are Xn times Ln plus Y naught times G is equal to Xn plus 1 times L, and there's no n here because all the streams are the same, plus Y n plus 1 times G. Now for the operating line, we're going to want to solve for Yn plus 1. Yn plus 1 is equal to L over G minus L over G times Xn plus 1 plus L over G X n plus Y naught. Okay, so now we have our operating line equation. So now we can basically draw our equilibrium relationship in our operating line and see where we go from there. Let's start solving our problem in Excel. So I've written down here all of the relevant problem information from the problem statement. So we have the inlet, outlet CO2 concentrations, as well as the inlet air CO2 weight fraction. And this I just got off the internet. And I also have the gas, the initial liquid flow rate, and the gas flow rate. Right, so what should we do? So let's start by drawing our equilibrium. So X and then Y. And then so X is just going to be an arbitrary reference value. So we'll start with 0 and then 0.01. And then we're just going to drag this down until we feel this is sufficient. And I'm going to stop here. And now for Y, the equation is simply Y equals 0.04x, so it's going to be x times 0.04. And That's it. Now, like we said previously, this is a weight fraction problem. A weight ratio problem. So we're going to have to convert this to ratios. So capital X and capital Y, and this is simply equal to X divided by 1 minus X. And there we go. And then the same is also true for Y, capital Y. There. So now let's just plot our equilibrium graph and see what it looks like. There we go. So now the next step, obviously, is to draw our upper line. Actually, I'm going to add a trend line, just so it's a bit easier to tell where they're going to intersect. There we go. So now the next step is to draw an operating line. So I'm going to do that here. And before we do that, we need to convert all of these fractions to ratios. So we're going to do that. So once again, the equation is the same, 1 minus x over 1 minus x. We're going to repeat that here. And to also calculate the operating line, remember that when working with weight ratios, we're interested in the inert flow rate, not the total flow rate. So we're going to need to calculate the inert liquid flow rate and the inert gas flow rate. And so the calculating this is pretty straightforward. It's just this. It's just the flow rate times 1 minus the CO2 fraction. So this gives us 796 kilograms per hour. And for the inert gas flow rate, this is equal to this, the gas flow rate times 1 minus the air CO2. And this is kilograms per hour. Right, so now let's calculate our operating line. So our operating line equation is like we derived earlier. So it's equal to the liquid flow rate divided by the gas flow rate times x, and then plus the liquid flow rate divided by the gas flow rate once again, times the inlet CO2 ratio plus the inlet air ratio. And now we just need to make sure that most of these formulas will stick when we drag them down. So there we go. And then, and the slope is actually negative, so let's add the negative sign there. And here we go. Okay, great. Now we just need to plot it. And there we have it. So if you look closely, the inlet air concentration is somewhere around here. And so our operating line passes through the inlet air and liquid concentrations, and it goes up until we reach equilibrium. Now let's bring this over to OneNote so we can continue solving the problem. Okay, now we have the first operating line and the equilibrium line imported into OneNote. So what do we do from here? So first, just for convenience, let's draw the air concentration on this graph. So it's y equals 0.00051. So it's going to be approximately. So this is just for reference, so we know where to stop our operating line. So for the remaining operating lines, what you're going to do is right where the equilibrium and the operating lines intersect, you want to draw a vertical line straight down until you reach the inlet air concentration. Now you can draw your next operating line, which is going to have the same slope as your first operating line. And it's going to have roughly the same, it's going to have the exact same slope. So draw something that's roughly parallel, and it's going to intersect the equilibrium line at another stage. So once again, you're going to draw a straight vertical line down until you reach your air concentration. Then you're going to draw another operating line. Now, just so we keep track, let's just take a note of where the final concentration is, and it's 0.0025, so it's about halfway. It's halfway between these two marks here. Now, the next step is, since we're getting pretty close to our target concentration, we note the last stage has no CO2 in it. So instead when we draw our vertical line, instead of stopping at the inlet, the typical inlet air concentration, we're just going to go all the way down to 0. And there we go. So now the last operating line forms an equilibrium past our target concentration. And so now we know that we need 4 stages in order to achieve the level of separation we need. 4 stages.